The work that I've been doing on this topic is done. The experiments are carried out at the Advanced Photon Source at Oregon National Lab. We use a couple of beam lines, the 1ID beam line, which is way over here next to the administration building. And once commissioned, we expect to be using the 20 ID beam line, which is the long beam line that goes outside of the storage ring building and houses the high energy X-ray microscope. We also have another HEDM instrument further upstream on the same beam line. So also, I have to thank the staff at Sector 1 who have been incredibly helpful over the years, and quite a few graduate students. So let me start with something that I think everybody knows about, grain growth in polycrystals. So I think everybody knows that when you heat up a polycrystalline material, you tend to coarsen the structure. You wind up with the larger average grain size after you anneal it than you started with. And I think most people know probably that the mechanism is expected to be curvature driven. This formula here says the velocity of a grain boundary is proportional to the curvature and the interfacial excess energy of the grain boundaries. So that's the expectation, and everybody knows that this has been verified, right? A long time ago, but it's been verified in bicrystals, which is a little caveat that turns out to be important. And maybe everybody should know that this had only been tested, it had not really been tested in 3D, in bulk materials. So the question is, how do you fix that? How do you investigate this internal evolution of a sample as you anneal it at high temperatures? So clearly what we need is a three-dimensional, non-destructive, crystal orientation sensitive microscopy. And if you think about that for a couple of minutes, you pretty quickly think of X-rays, since they penetrate into the bulk of the material. They exhibit crystallographic diffraction patterns that we understand quite well, and there are lots of them that are generated at the high energy synchrotrons. This is just an example of a problem. There are many similar problems that have to do with the material's properties and responses that are microstructure sensitive. So I'm just using this because there have been some recent developments that I'll tell you about. So why high energies? So what I mean by high energies is photon energies above 40 kilovolts, which implies that the wavelength is substantially sub-angstrom. And the effect of the short wavelength is to compress reciprocal space. Let's look here. This is basically Bragg's law. Sine theta is lambda over 2d, the spacing of planes in your crystal structure. So as we reduce lambda, we reduce the angles, and this Bragg angle is 1/2 of the scattering angle. That is the deviation of the diffracted beam from the direction of the incident beam. So it's in that sense that reciprocal space gets compressed when you go to high energies. Also, high energy X-rays penetrate more material, and by tuning the energy, we can get transmission through millimeter samples over spanning most of the periodic table. It's not always possible, as the example of tungsten down here shows. But if we can get through a substantial amount of material, then we can call X-rays a probe of the bulk of the sample. So if we want to look at internal microstructures, high energy X-rays are a way to do it. Also, as you go to high energy, you get less damage per signal. So both the signal and the absorption cross sections go down, but the absorption cross section goes down faster than the signal does. So you can actually study relatively soft materials with high energy X-rays without introducing a lot of damage. And the last point, of course, is that there are lots of these X-rays available, and that's shown in this Moore's law plot over here. It's thanks to John Mao for this image. In blue, dark blue, is a representation of Moore's law for computational power. And that computational power is increased by about 12 decades. That is 12 factors of 10 in computing speed over 6 decades of time. By comparison, the red curve is for X-ray sources. So this brilliance is a combination of factors that make the X-rays useful for the kinds of experiments that we're doing. And that has evolved over the same 6 decades by 20 orders of magnitude. So we have lots of computing power, and actually we use that in this business. We also have lots of X-rays, which is very convenient. So that's why we want high energy X-rays. What's the experimental geometry? So there are 2 flavors of AGDM that I'll talk about. This first one is the near field variety, and I'll spend most of my time with that technique and the results from it. In order to do the near field measurements, we focus the X-ray beam down to a line focus. So it's about a micron and a half tall, and a millimeter wide beam. And the millimeter wide beam then is, well, some of it's transmitted through the sample here, shown in green. And then we put area detectors downstream of the sample to capture diffracted beams. So that's shown, this little black guy is diffracting at a particular omega value. We're going to rotate, okay, we've got a monochromatic beam, so we're going to rotate the sample to achieve the Bragg condition for various HKLs for each of the grains in this cross section. The sample is placed between 5 and about 15 millimeters downstream. Sorry, the detectors are 5 to 15 millimeters downstream of the sample or of the rotation axis. The sample is centered on the rotation axis. Yeah, so we capture images over small rotation angles. Traditionally, we integrated over 1 degree for each image. We've taken data sets with as small as an interval as 0.01 degrees. A quarter of a degree is sort of standard now for our orientation mapping measurements. And we collect these images over 180 degrees of rotation. For the far field, as the name implies, the detectors shown here are placed of the order of a meter downstream of the sample. So these guys capture multiple diffraction peaks, multiple HKLs in parallel. And this arrangement of 4 medical imaging detectors, these are each 40 or 60 centimeters in size. This arrangement is made so that you can get out to higher angle scattering. Reciprocal space here I refer to as Q space. And that higher angle scattering gives you better strain resolution. So the far field measurement is actually quite sensitive to small strains, as small as a few times 10 to the minus 5. So here's a look at what the detector images look like. If we start over here on the right, The far field detector is far from the sample. So as the sample rotates, these images are integrated over 180 or even 360 degrees. We see the familiar rings from powder diffraction, the Tobias-Scherrer rings. And if this was an in-person talk, I would ask for hands on who knows what crystal structure this is. The answer is it's an SCC crystal. You can tell from the spacings of the rings. However, the diffraction spots that are on this ring, on each of the rings, you can just, if you blow it up, you can see that they're not exactly on the ring. There's small displacements from the ring. And if we go back over here to the near field schematic, those displacements are first due to the fact that the grain that's doing the scattering is not necessarily right on the rotation axis. So that gives a little displacement. If you think about taking this far field image, well, the far field detector, and bringing it closer to the sample, the size of these rings will get smaller and smaller until eventually those displacements due to where the grain was when it lit up the Bragg peak becomes comparable to the size of the ring. So the real space position of the grain comes into play as you bring your detector closer to the sample, and that's what we do in the near field. So in the near field, you don't see the rings; you just see a conglomeration of diffraction spots. And there's a major difference between these two in the scale of these two detectors. The pixel pitch over here on the medical imaging detector is 200 microns, while it's a meter away. Here, the pixel pitch is about 1.5 microns. And as I said, it's between 5 and 15 millimeters away. So here, the positions of the spots don't really tell you anything. In a single image, there's very little information. And in fact, what I always say is that our data are highly encoded. Figuring out the microstructure from these images is not a trivial task. But think about what happens as we rotate this one little grain around the y-axis here by omega. As it moves around, different Bragg peaks are going to be satisfying, the different planes will come into the Bragg condition to generate diffracted peaks just from this one grain. So there are multiple spots in this image from a single individual grain, but then there are lots of grains in the cross section, of course. So that generates this whole conglomeration. So untangling this, figuring out both the scattering geometry, that is the 2 theta angle, the scattering angle, and the orientation of that scattered beam eta is a pretty serious computational problem. So here's how we solve it. nice powerful workstations with good powerful GPUs. So Hexamap is the name that was generated for the current version of our software. It stands for High Energy X-ray Orientation Mapping, and it's sitting on GitHub. It's available. Most people feel like they need a little help getting started with it, but that's not too surprising. So what we do is we forward model the measurement. So we voxelize or mesh up essentially the illuminated plane into voxels, volume elements, and then we search for the orientation in each element that generates diffracted beams that overlap the observed images, the observed spots on the detector. So it's rather brute force, but it's also very flexible. We're not insisting that the grains be good single crystals necessarily. And I'll show you that there's a lot of information you can glean from the data by doing the reconstructions this way. I think the rest of this, well, just as an example, in one measurement, we had to reconstruct something like 35 million voxels to start to do the science of the measurement. So when we run hexamap, we get an orientation map by doing successive layers, cross sections or layers in the sample. We generate a three-dimensional microstructure map. So here the colors are coded to the crystallographic orientation. It takes 3 parameters to specify the rotation from the reference frame of each individual voxel. And so we just map those 3 parameters to RGB colors. So this all started at 1ID. Here's the door to the 1ID-B hutch, which is where we developed this stuff originally. And I'm going to show you some data from way back then. And here's a crowd of people squeezing inside of the hutch. Clearly, Chris Heffron back here is the one who's trying to do something with up here in the sample area. Yan Gao from GE Global Research is sort of looking over the shoulder, seeing what's going on. Ulrich Leonard is the staff scientist who basically put together the hardware for doing all these measurements. His contributions are huge. He's now at Petra 3 in Germany. John Lind is now at Livermore Lab. And Riju Pokharel is our, sorry, I'm looking at the back of everyone's head here, but just wanted to show you that the collection of folks who are at a typical data collection run. So, okay, lots of computers, lots of screens to look at, just visual cameras to look inside the hutch, like up here, and to look at and analyze the diffraction images. That's a near field measurement right there. You can see the diffraction spots. And then to give you an idea about how this business has developed, here's a picture of Frankie Lee with 2 HEDM compatible, near field compatible loading devices. So if you want to rotate your sample, you can't necessarily put your sample on an MTS load frame because you can't rotate 180 degrees without running into the detector. So the first tensile measurement that we did was on a little copper wire. He's holding the load frame between his fingers. And that probably cost a few $100s, and we built it right at CMU. But as things developed, this is the second loading system that's near field compatible. And I'll show you a blow up of the business area here. But this is a marvelous piece of high-tech equipment developed by Pulse Ray, which is basically Basil Blank, and AFRL, the Air Force Research Lab, paid for this. It was, I hear, something like $1 million. Currently, we're up to RAMS 4. This is RAMS 1. So this whole business has attracted a lot of investment. So here's the business section of RAMS 1, I believe it is. So these are the grips, and there's no sample in it right now, but you can see here the beam block sticking in on a little goniometer from the side. This plastic piece here holds a little lutetium aluminum garnet sample crystal, which is a scintillator. So it absorbs X-rays and emits visible light, which goes into a lens, which goes back to a CCD camera. More well, currently we've graduated to CMOS instead of CCDs. And then up below and above are the precision air-bearing rotation stages, which, much to Basil Blank's credit, are essentially perfectly aligned. Okay, so that's kind of a brief look at the hardware and the methodology. So let's get back to grain growth. And to do that, I'll show you this image from a 2010 marathon beam time that we had in December. You can see that it's December in the picture. So again, this is Ulrich Lehnert. This is Frankie Lee and Chris Heffron. And of course, Santa Claus stopped by the beam time to reward us for working right up to the time when the synchrotron went down for the holiday. So in that run, we measured a high purity nickel sample, which was annealed 6 times. So we measured the same volume of material 6 times after successive annealings. And that data, when was reconstructed using Frankie's C++ code. So Heffron, Lee, Ulrich Lehnert, and myself did the data collection. And if Rishu's watching, I hope I'm remembering that you hadn't joined the group yet, so you came in later. No, that's Riju Pokharel, who's our collaborator at Los Alamos now. So this data went into 2 PhD theses, and a variety of analyses were done, but it was all pretty puzzling. And in fact, John Lynn did some work while he was at Livermore, trying to get a better alignment of all the data sets. Quite a difficult project, and quite frustrating for a long time, as you'll see. So I left out a critical point here. Gregor eventually convinced NSF to give him and Kaushik Dayal in civil engineering and myself in physics, but primarily Greg and his group, a grant in 2018, basically to address this then 8-year-old data set. It's pretty unique, or was pretty unique. Finally, 2021, we published a paper on this in Science Magazine. And the title of the paper says it all: grain boundary velocity and curvature are not correlated in nickel polycrystals. So the reason the data were so puzzling is because that curvature-driven rule that we started off trying to validate, well, we finally decided that the data were right and the rule was wrong. This by following 52,000 of order 52,000 grain boundaries in the crystal. This just says the grain boundary velocities and curvatures are uncorrelated, and we found strong correlations between the boundary velocity and the 5 macroscopic parameters that specify grain boundary crystallography. So grain boundaries live in a 5-dimensional space specified by the relative orientations of the 2 grains on each side of the boundary, and the orientation relative to the crystal axes of the interface plane. So that's a 5-parameter space. And it turns out that is relevant. So the data weren't just noise. There was actually systematic trends in the data. And in this paper is basically a negative result, saying this doesn't work. But we point to the fact that there are anisotropies, that is to say, variations in grain boundary energies as a function of those 5 parameters. And most simulations, for example, assume that the grain boundary energy is the same for all the planes. Basically, the work implies that there's a need for a new model of grain boundary migration. So just to illustrate the negative result, here's is plotted the grain boundary velocity as a function of the curvature of that grain boundary. And again, there are 52,000 points. I'm not sure if they're all here or not, but that's not a very strong correlate. Question? Okay. Okay, but then my claim is that the data isn't just noise, that it's showing real behavior. And this is the average energy per volume, that is to say, the average grain boundary energy per volume as a function of annealing time. And here are 6 data points. And yes, the grain boundary energy is going down. It's just not following the rules that we expected it to. And if we take into account the anisotropic energy of the grain boundaries, there's an increase in the amount of reduction, if you will, of the grain boundary energy. And I think, given the time, I will skip over this mostly, but this is just demonstrating that the grain boundary velocities in these plots has a systematic dependence on the orientations of the grain boundaries. If there are questions and interest, feel free to ask me at the end. So since that Science Magazine negative statement, we've published a couple of papers through further analysis, and this is one in Scripta, in which we propose a grain boundary replacement mechanism that would take place with annealing. And that's illustrated here with this one individual grain in 5 anneal states. And the point to focus on is this gray boundary here, which has a low interfacial energy compared to the other boundaries that you can imagine are present here. Each one of these, when the color changes, you're looking at a boundary between a different neighboring crystal. But this flat twin boundary, in fact, it's a twin boundary, increases in size consistently. It doesn't move according to curvature because it's quite a flat boundary compared to some of the other boundaries. So this is an example of this grain boundary replacement. There's sort of a lateral growth of a grain boundary because it has lower energy than its surrounding boundaries. So by curvature, you wouldn't expect this to be moving very, very much. And so this is sort of an alternate mechanism, an additional mechanism for the boundary network evolution. Okay, the above results appear to be generalizable. That is to say, we've also taken data on a polycrystal and iron sample, and analysis gives quite comparable behavior to the nickel. Iron is less anisotropic than nickel is, and so the variations are less, but it still had qualitatively the same behavior. And even in a ceramic strontium titanate, this is work by Amanda Cross's group. Amanda's a relatively recent hire in MSc here at CMU, and again, this doesn't appear to be an example of nice, simple curvature-driven growth. So it's a good idea to have 3-dimensional data. And again, this is just one example of a material science problem where you need to see the evolution of the microstructure inside of a bulk material. Okay, this is a recent paper. Actually, this just came out this week. I was interested to see that the CDAC folks already have a link to this on the on the invitation to this talk. This just came out this week. So this is the impact of grain boundary energy anisotropy on grain growth. This is a simulation, but it's a simulation that starts with the measured structure. This is the anneal zero state, the initial state that we started with, and then this is the microstructure after one annealing cycle. And there's this little twin boundary down here. You have to look pretty carefully. This red twin boundary. It was pretty wispy in this case, and it grew a bit in this case. And then these two are the results of simulations. This is an isotropic simulation in which all the grain boundaries have the same energy, and that twin goes away. Whereas when we use basically an interpolation formula for the grain boundary energies, and put that into the simulation, and that was a major development in this threshold dynamics simulation, is being able to put in the different energies for different kinds of grain boundaries. This looks actually amazingly like the measured data after annealing. Okay, so enough for grain growth. That may not be the most urgent topic in CDAC, but I used it as an example of what you can learn when you do these three-dimensional measurements. I've got a couple of additional examples that I'll go over quickly, but this one is actually relevant to the project that Tony Rollett and I will be doing together with Riju Pokharel at Los Alamos. So this was a measurement of shock deformation in copper. Most of the work on the experimental data is by David Benash, and this is a paper in 2016. So what we did here is measure a volume of a 1 millimeter diameter piece of copper, measure the microstructure, and then we sent it off to our collaborator, John Bingert at Los Alamos. And he did a shock deformation, a flyer plate impact deformation of our poor little sample that we had carefully measured and struggled with. And he managed to find it after the shock and get it back to us when we were already at the APS, and he got it there in time for us to do the measurement of the same volume of material after the shock deformation. This is a tomographic image of the sample, and where these little black dots actually corresponds to voids within the volume of the sample. And so the goal here was to try to associate damage resulting from the shock to microstructural features. So let's see. This is actually an image of the initial state microstructure. This is a little piece of microstructure that sticks out from this the cut here. The data actually span the whole circular sample. So you can see that this little cluster of grains with different colors, different orientations, overlap the region in the sample where we see lots of voids forming. And yeah, this is a top-down image of the voids inside the sample. If you blow it up, you can see that they're color-coded as to where they are in the z-axis in the vertical dimension. So yeah, so this guy goes down there. Voids are in the neighborhood, and I believe David is showing here a little region close to at least 3 grains where voids occur. And further work by Tony's student Lieberman um, uh, searched for correlations with the microstructure, and he managed to find weak correlations between the positions of voids with boundaries where there's a large difference in plastic activity. But as Tony said the other day, this needs validation. And so in the CDAC, our plan is to do a more systematic study of similar responses in titanium. Titanium is more anisotropic, so it should have a greater range of sensitivities in the microstructure to voiding. And really, the bottom line question is, does microstructure matter for the in-shock deformation? Can we find local sources for deformation or for failure within the shocked volume? So I'm hopeful actually that titanium will be a good material in an additional sense. The copper is quite soft, and it had regions like over here. Let me back that out. This region didn't get reconstructed in the deformed state because of the large plastic deformation. So my hope is that titanium will be less severely deformed, and will therefore allow us to do a more complete reconstruction after we shock deform it. I'm sure there are many questions on this topic, but I'll move on just to show you that there are a variety of other kinds of things that are interesting to do with these microscopies. This is a measurement in which we looked at recrystallization in an additively manufactured 316 stainless steel sample. And let's start over here. When you do laser powder bed fusion, you typically wind up with a very complex, I'll say messy looking microstructure. And it's a state of the material which doesn't allow the standard straightforward HEDM reconstruction. So these images show successive anneal states of this sample. And initially, actually after one anneal cycle, we see a sparse, pretty random looking distribution of grains. And to clarify what's going on here, when we do the forward modeling reconstructions, right, we're optimizing the orientation so that it hits as much diffraction intensity as we can find. So we wind up with a confidence map for the optimum orientations. The confidence is just the fraction of simulated Bragg peaks that actually do hit experimental data. And that's pretty low over most of the sample initially, with these bright spots corresponding to where grains are, measurable grains are. And as we anneal, the structure fills in as you'd expect for recrystallization. And so you can make these wonderfully beautiful little maps of grains that are inside the material, but the rest of the material is deformed, while these guys have formed quite high quality single crystals. And another one of the things that we looked at is twinning. 316 stainless steel is STC, and it exhibits strong twinning, and we could watch the twinning as a function of annealing. This is one particular twin-related domain. So all of these different colors correspond to twin-related crystal structures. And as this grain grows, additional twins form. So these are I think what Tony would call growth twins. Um, okay, and I should point out that in spite of the constraints of the near field measurement, that is to say, you want to be able to rotate the sample, but you would like to have an in situ environment. In fact, we were able to do that in this measurement. We have this little fist-size furnace. It's an infrared furnace that heated the sample while it was on the rotation stage, and it even allowed us to monitor the diffraction patterns as a function of time at elevated temperatures. We did the measurements that led to these images at room temperature, but we could monitor what was going on and stop the annealing at the desired times after a certain amount of development. And this is actually a far field image, and this is our thermometer. It's always hard to measure these things at samples at high temperature. But if you look quite closely, the green rings are where this Debye-Scherrer ring or these Debye-Scherrer rings should be at room temperature. And then at high temperature, thermal expansion takes place, and that shrinks the rings. And you see that if you look closely, the white dots are slightly inside of the ring. And by calculating the thermal expansion, we can back out the temperature. So this was data collected at nominally at 1,000 centigrade. The sample was actually a bit hotter than that. Last thing I'll hit you with is just something that's, well, we have a proof of principle of this sensitivity to intragranular strain variation. So as you strain the grains, the unit cell gets deformed, and that will move the diffraction in reciprocal space. And the question is, are we sensitive to those kinds of small variations in the unit cell? And in particular, are we sensitive to the variation in the strain state within grains? So, well, let me just show you what the signal looks like. So this is a Ti-7 aluminum sample. Here's one particular Bragg peak. And this is initially when the sample was not under load. And then we loaded it to about 200 megapascals, and this one peak splits up into three. So these are three successive omega intervals into which this peak gets divided. And in fact, if you add up the intensities of these three, you wind up with an image that looks just like this. So this is a signal of strain, and my graduate student Yufeng Shen put together an algorithm to do an optimization of a deformation tensor, that is to say, a 9-component strain and rotation tensor. And these images just show you the one component of that tensor. First, in the initial state, where the strains are all clustered pretty close to zero, and then under load we see larger average strains, and in this case a tensile strain. Over here it looks like a compressive strain, and well, okay, so that difference, for example, Armin Bodwin suggested that the sample was a little bit bent, so that when we pulled on it, it compressed one side here and stretch the other side here. But you also see that there's a variation within the grains, and that's what we're after. So this is published work. It proves that we have the sensitivity, and we also show that we match simulated states. So we have a good faith in this reconstruction procedure. And it gets more dramatic. Here's the uh, these are all images of one Bragg peak in another Ti-7 sample. This time we measured it with 0.01 degree integration intervals, and you see that this one Bragg peak is spread out over a large number of images. The smaller rotation interval ought to lead to higher strain sensitivity. So I suspect we can get down around 10 to the minus 4, maybe even below. And again, if you add up the intensities, yeah, so L1 is refers to the first detector position, L2 is the second detector position. And if you add up these intensities, you wind up with something that looks very much like the projection of a grain cross section. Okay. So one thing I'd say is that this business is pretty wide open. I mean, there are beamlines in at ESRF, and now we'll have 2 or 3 instruments at the APS. So it'll be easier in the future to get beam time. And modeling or predicting microstructure sensitive properties and evolution really demands these kinds of structures, these kinds of studies. Don't believe what you haven't measured or that hasn't been measured. And there's a growing suite of methodologies and capabilities. There's the techniques that I showed you. There's the diffraction contrast tomography. There's even a laboratory-based version. And then dark field microscopy is something that's being developed by Henning Poulsen and company at the ESRF. We've worked on combining the HEDM measurements with Bragg coherent diffractive imaging, which I haven't said anything about, but we have a paper in preparation and a prior paper already published. This is restricted to nanograins at this point. One thing we're trying to do together with people at Argonne is push the capabilities of the CDAC method to larger grain sizes. And basically, what will the upgraded synchrotrons let us do? We're going to have quite new beams, and I'm looking forward, even in my retirement, to watching other people develop new capabilities. So with that, I'll quit, and thank you very much for your attention. And I'm happy to take questions.
Yeah, thanks, Bob. Great talk. This is really impressive data. And this technique has a lot of potential for CDAC. And I can guarantee you that CDAC is, in fact, interested in grain growth and grain boundary evolution in general as a function of pressure and temperature. So time for questions and comments. Just unmute yourself, put your comment or question in the chat. Raise your hand. Maybe to start with, I kept wanting to ask or was wondering, what the potential will be for APSU, and you hinted at it at the end with, the coherence. So could you say a little bit more about that? I mean, obviously we want to go beyond just nanoparticles, but
right.
Plans for using the capabilities of APSU?
Well, happy you asked. Let's see if I can share the right screen here. You have my conclusion slide?
Yeah, that's great.
Okay. Okay, the APS upgrade. So basically the whole storage ring has been ripped out and a new storage ring put in its place. And one effect of the new storage ring is that we're going to take an electron beam that used to look like this, that is extended in the horizontal direction, which is the in-plane direction as the electrons circulate around the ring. So it's spread out in the in-plane direction, and it's sharp in the vertical direction, it's going to take all that electron beam and put it into a little spot like this. The result of that is that we'll be able to, well, at the smaller source size, we'll be able to focus the X-rays better, but it also leads to increased coherence. So, for example, yeah, let's see. So most of the BCDI measurements currently are done at 9 kilovolts, 9 kilovolt photon energies, and this is the maximum coherent flux that you expect to get. So the red line is the, well, now prior APS, and this blue line is the new APS. And the point of this slide, this image, is that at above 40 kilovolts, one will have the same sort of coherent flux as we have had at way down here at 9 kilovolts. So this means there's a huge improvement in coherence. So the X-rays will be more coherent. Another way to say it is that the coherence length will be larger, and that will allow us to look at larger grains. With the caveat that as you go to larger grains, the fringes that you're trying to measure get closer and closer together. So these little bumps of intensity here are the truncation fringes from a crystal which has a nice faceted surface. The Fourier transform of a step function is a whole bunch of oscillatory fringes. So this gives you an idea of what an individual diffraction peak might look like on a CCD camera. And this is just a bunch of images that you obtain by rocking the sample through a nominal Bragg peak position. So bottom line, the flux will be there for measuring coherent diffraction at larger energies, and in particular with the high energy X-ray microscope, that is that long beam line in the end station, you'll be able to get way far away from the sample with your detector, and therefore be able to resolve very rapid truncation fringes. And the truncation fringes are sort of the handle that you have on the when you go to do the phase retrieval from these things to regenerate the shape of the grain. If I'm not making sense here, ask me questions. I may be using language that's either familiar or quite unfamiliar.
This is great.
Does that suffice? I mean, there's a lot of potential here. In fact, one of the things that we'll have to do when the beam comes up is figure out whether it's easily compatible with doing AGDM measurements. The coherence may get in the way, but there are solutions already planned for that. But we'll see what the beam looks like when it comes up.
Great. Yeah, that higher energy range is also very important for diamond cell samples because we need to be above, roughly 20 keV for good measurements in a diamond anvil cell.
Yeah, very good point. Yes. Yeah, I don't doubt that one will be able to do these measurements. Well, there are caveats. Passing the X-rays through multiple materials can lead to decoherence. Right, different parts of the wave go through different materials, and therefore they get out of phase. So the nice uniform phase front can be perturbed by passing through different materials. Um, so it may not be trivial, but I don't doubt that it'll happen and problems will be solved.
Well, some proof of principle experiments were done back in the 2012, 2013 period with diamond cells with APS.
Okay,
Yeah, so we're pretty confident we can do some of this.
excellent. Yeah, yeah.
Great. More questions, comments?
I think there was a question in the comment section, Russ.
Okay. Let's see. Oh yeah, from Cheng Yong. Cheng Yong, you want to speak up?
Yeah, so you can read my questions. It's a very
Yeah, go ahead.
explicit. Yeah, but yeah, this method is great, is known, and but the one of the challenge that we face as high pressure science, like samples in diamond amber cells, like our grains is typically have like some sub-micron size to the a few microns is very typical. And sometimes this approach, as you described in the first few slides, has basic principles of near field imaging and the far field imaging, has a sensitivity to the distance and like a position and like a size of grain and so forth. And I just wonder, in your knowledge, that is there something that we can identify what parameters may most affect that determining those sensitivity to the size of grain or spatial resolution, and where could it be a possible improvement to achieve our goals to challenging that like a different like a size of grains, including that the submicron sizes.
Yeah, yeah, that's a very good question, and something of considerable interest. So let's see. One part of the answer, I think, is that one can make progress on pieces of that problem. Um, we, for example, took some data on some uranium dioxide nanograins, and we used the far field detector, and we found that yes, we could measure orientations. One of the things that I've been playing with in my spare time, again in my retirement, is looking at some near field data that we took. So near field, using the near field geometry with a detector up close with a high resolution detector. We can see spots from individual nanocrystals, and I believe that we can determine centers of mass of those grains by using that near field quote unquote data. It's just a matter of the precision of back extrapolating to figure out where the grain is. So by doing that, we can identify positions and orientations of grains that could then be looked at with BCDI. And that was our motivation for doing that measurement. I don't have the result out yet, but I'm confident that we can get good center of mass positions which will allow us to look at, for example, a polycrystal of nanocrystals, the polycrystalline nanocrystal array. Not without challenge, but I think we can actually do that kind of thing. The limitation in the standard near field measurement is just the detector resolution. So one solution to the limitation of the pixel size, essentially, of course, there's also the intrinsic resolution of the scintillator crystal itself, whether that spreads the signal out some. Yeah, so one solution to the problem of the pixel size is that one can put an optic in the diffracted beam. And that's essentially what the dark field X-ray microscopy does that Henning Poulsen and company are working on at the SRF. They claim resolution down to at least 100 nanometers. I'm not sure whether it's better than that. But that's an
using
expensive measurement because you have to position your optic and your detector for a single diffracted beam.
So using dark field imaging reaching to the 100 nanometer resolution. So that's quite impressive. Okay.
Yeah, it is. Yeah, I agree.
So I see. So like I tried myself this method one time in the past, but the kind of pathetically failed because exactly that you mentioned that the near field camera's resolution and actually the size of field of view of those phosphor screens are really like limited to play with that enough number of the grains, and because it was blocked by the diamond ambers kind of things. We couldn't bring that near field detector as closest possible to the sample, then that inherently blocked at the all basic idea of how near field imaging is working to determine the grain positions and some kind of a thing. So there are some limitations, but now I get it. Some fundamental point that if there is a way to improve the near field images resolution and the pixel size and so forth, then there might be some way to improve. There is some one spot. Okay.
New CMOS detectors have smaller pixel sizes, so we're looking forward to working with different detectors post upgrade.
Okay.
So we can keep you posted on that.
Do you happen to know that in the Hexam beamline, the sector 20, that the long straight beamline that you show in the first slide, that what kind of a spatial resolution that instrument is aiming at?
Well, everything wants to be below a micron.
Okay, below micron. Good.
Yeah. So the point of the long beamline is to optimize the focusing optics, and so to be able to get as small a beam as possible. And when you get a small beam, you're also going to get a more highly coherent beam as well. So the two basically go together.
Gotcha.
So it'll be interesting to see what you can do in Fourier space versus what you can do in real space with the HEDM kind of measurement.
Okay, gotcha. Yeah, thank you for answer.
Yeah, thanks for the questions.
Thank you. More questions, comments? Well, if not, thank you very much, Bob, for a great talk.
Thank you very much.
Next phase. Thank you all for joining us.
Take care, everybody. Thanks.